So thanks so much, everyone, for being here. I mean, night, day, morning, whatever part of the world you are in. I'm in Italy, so it's like mid-morning today. We're talking about Bauplan and our purpose-built FaaS system for data workloads. Bauplan is a tiny but mighty company based in New York and San Francisco, and is backed by historical Silicon Valley VC and a bunch of people in the data and AI ecosystem, like Professor Chris Red Stanford and the inventor of Arrow, Wes McKinney. I promise you that the name dropping will be relevant in what follows, so bear with me. If you have more questions about us or the company, please feel free to reach out to me at any point through LinkedIn, email, or whatever you like. If you have to take away one single thing from today, is this one. So Bauplan is a system in which we co-designed the runtime, so functions as servers runtime, and the abstractions, the way in which you actually express functions and how they chain together. And this weird choice, which will be the main topic of today, is, if I have to sum it up, the result of two impossibilities. Impossibility number one is taking an existing DAG abstraction framework, they're familiar, for example, with Airflow, and add a runtime to it. And we're going to see why. And the second impossibility, taking something like Lambda or OpenWhisk in the open source side and adding data lake and DAG functionalities. So we decided basically to start from scratch, of course, incorporating some of good ideas from other systems that exist, and design both the runtime and the abstraction together. So we're gonna do a small overview of why DAGs are important in today's ecosystem. I know already people are fed up with AI based on the word cloud, so I'm gonna keep that brief. We're gonna talk about a bit the abstraction and the architecture of Bauplan, and then we're gonna actually see live run in Bauplan, explain what's going on behind the scene, and conclude with a lot of the things that we need to do in the future. So if you're familiar with, or if you ever wrote a data workload, a data application like analytics application, business intelligence, AI, you probably know that data is not given to you, notwithstanding the original meaning of the word datum, is not given to you in a ready-made format. Like you can just go on your S3 bucket and do AI with that. So what typically happens for people doing machine learning, AI, or analytics is that they take the data that has been collected by some tracing process or some pipeline. They transform it, they clean it, they aggregate it, and then put it basically into a dataset shape so that you can do stuff with it. In this example, which will accompany us for the rest of the talk, so we start with some source data, is like just a log of transactions that happen to this imaginary company. Then we run a function, in case a SQL function, that produce a selection. So we're filtering here for countries based in the European Union. And then we do some other transformations, in this case in Python, and we basically produce an aggregate, which shows by each country how much revenues we have. And so the immediate question you may ask is like, well, this looks like a perfect case for FaaS and serverless. Like everything is a function, you can just chain them together. We don't have to worry about the underlying operating system. If I go back to the definition of the keynote, what's not to like? So can we just take what we have, like lambdas, for example, and make it DAG aware? And to understand the data workloads a bit better, we need to know three main important features that are not exactly parallel to what you may have in typical FaaS use cases. The first one is the need to scale up. Industry traces place the P99 for memory consumption of data workload between 50 and 200 gigabytes. Second, when you move data, you move a lot of data. So functions in the data words are not 200 millisecond function that you need to run a billion times over 10 seconds to go back to the previous use cases presented by the keynote speaker. Are actually the opposite. Like you move hundreds of millions of rows, not so much concurrency, there are many hundreds of millions of rows at the same time going on, but you need to move very, very big data frame between of them. And finally, data is open-ended. Most data projects have actually very, very complex business logic. So a function may take seconds or minutes or sometimes hours to run. And you don't really know what you're going into until you find out. So compared to typically, normal software projects, which are well-scoped and well-defined, data projects are actually open-ended. So the key to open-ended project, the key to success is actually to iterate as fast as possible. Try a library, try a package, try different versions, try a different subset, and you somehow build your intuition of what the data is telling you by keep on iterating. And so the question of like, can we take something that exists and reuse it is a resounding no. If you take the typical serverless platform existing, like for example, in this case, Lambda in the commercial world and OpenWhisk in the open source one, you find the use cases for which these are designed are completely different. Like, a lot of tiny small function running relatively simple business logic for hundreds of milliseconds. This is a page from the O'Reilly Open Whisk manual. And most of the example you find there, actually all the example you find in that book, are things like this. Send an email, read a message from a Kafka queue, and glue code, move this somewhere else, right? And in fact, if you look at the features of this platform, you're going to find it a very small memory footprint. These are the current numbers, which are like 100 times smaller than the one need to be for data. They're very small IO size, which means that you cannot pass data between these two functions. And you need to basically use object storage to do that. We're going to see why there is a problem. And finally, they're mostly built for deployment, not iteration speed. As we're going to see later, rebuilding a function in Lambda, for example, if you change your mind about which versions of pandas you want to use, may take you a few minutes. So if you multiply a few minutes for 10 times that you need to try new versions or new data, you're going to basically waste hours of your day just waiting for AWS to do something for you. So we cannot reuse what we have, so we need to build something new. And this new thing is called Bauplan. So the Bauplan architecture is kind of a mix in between a normal FaaS, data platform, and a data platform in the cloud. Why? When you run a Bauplan pipeline, you use your computer, you pip install Bauplan, you just do Bauplan run through a CLI or a Python SDK, whatever you want. And what happens is that your code gets shipped to a first multi-tenant platform that is in our own cloud account. This multi-tenant platform will parse out the code and it will do some planning, which again, it makes it more similar to a data platform than to a Lambda. And we're going to see why planning is necessary. Once the plan is done, we call it the physical plan in analogy to the database literature. The physical plan is sent to available workers, which may well reside in our customer AWS account. Actually, they all do. This is why Bauplan initial customers are very large enterprises. And while people are typically okay in sending small endpoints like typical Lambda endpoints somewhere else, people are really protective about their data. So people do not want their data to ever leave their VPC. So the structure of Bauplan is not just very flexible, but it allows people to run data processing workloads within their architecture. We never see anything that is not metadata, and all the data and all the surface in common between our own code, the system code, and the customer data is in an AWS account that we don't have access to. How do we express computation in Bauplan? So we can see here, typical example, on the left we have Lambda, and on the other one we have Airflow, and you're probably familiar with both of them. So this is a typical data, a simplified data function in both cases. So as you can see, at least in Lambda, you have a concept of infra as code. So in the case you prepare a Docker file, which you can ship then to AWS. So you use that to build your container, ship it to ECR, and then you can pick it up with Lambda. But it's very manual. So you need to know what a Docker file is. You need to know the Docker syntax, and you somehow need to go through the specification of what happens when you want to run your function. The inputs of all these functions are generic. In the case of Lambda, is the standard signature that you just get. In the case of Airflow, is a standard Python function. You can put it whatever you want. In this case, in this pre-processing function, which is taken from the AWS best practices for machine learning pre-processing, it just basically S3 path. And the S3 path are useful. Why? Because you can't really return the result of your pre-processing like you do in a normal function. Like in a purely functional idea, you get some data frame in. Remember our example. You get some data frame, you transform it, you pass the data frame to the children function, and so on and so forth, right? But since you can't really move this amount of data between functions, neither in Lambda or in Airflow, what happens is that you save intermediate data frame basically as a side effect, right? So there's a function that is completely opaque to the caller that somehow store the results in S3, and then the children function gets, naming convention or pointer to that part of S3, and then you can go on in your merry way to do your pipeline. So can we design better abstraction for FaaS? And our answer is like, well, we should be able to do so, right? So if you say the same code in Bauplan, okay, this is one file just for ease of use in two different boxes. You see that we have pure Python function. If you see on the left, there's euro selection, the second function in our DAG, and on the right, USD by country. The first thing to note is that it's really infra as code. There's no YAML, there's no weird file that you need to know. Once you start a Python function, you can just put into the decorator the version of Pythons and whatever packages you want to use. And that's enough for the system to go on. So you need to learn Docker. You don't even have to have Docker installed in your computer. The second difference that you can see here, that inputs are not generic. The only inputs that you have are basically data frames or models or tables, whatever lexicon you want to use, depending on the on your literature of reference. So for example, euro selection, remember, is the second function of our DAG, takes as input transaction and specify a list of column and a list of filters that you want to apply to the input. And that's enough for the system to be able to produce this data inside the body of the function. And finally, very important, function do actually return the result of the processing. So in the case, you see that the data frame returned by euro selection on the left is what goes into input of USD by country in the right. You see there's a naming convention, so USD by country takes the name of the parent function as an input. And so the system knows that whatever tuples, whatever hundreds of millions of rows goes out of euro selection, that needs to be the input for USD by country. So what happens when you run something in Bauplan? So now you see how we express the computation. What happens when you run? And again, the general thing that I want you to take away is there are like 3 phases of this, and we're going to see them in a minute. But just to have the high-level picture, when you do a Bauplan run, first thing the system does is planning. So we need to take whatever the user has given us and make an actual plan of what we need to execute. Second, we need to set up the environment. You need pandas, you need DuckDB, whatever you need. And third, we need to move the data. Right? You need to, when you want a transaction table because you specified as an input, we need to make sure that that transaction table is available to the function when the function actually runs. I'm going to move away from my slide for a tiny bit, and I'm going to just open my IDE, my Visual Studio, and I just wanted to show you what does it mean to run a Bauplan code. So this is the Bauplan, this is a Bauplan project, so it's code that sits in my IDE, in my local computer. You see the decorator that we have discussed? Okay, this is using the famous taxi dataset that everybody uses in data science to make examples. And so this is a DAG that takes the taxi table as input, does some pandas normalization, there's some printing that you want to do, and then there's a child function which takes a join, basically joins the taxi zone table and the function that we just defined. And in this case, it just uses DuckDB to do some processing. When you Bauplan run, you can see here in my terminal, this code gets shipped to the cloud. None of these run locally. So all of these runs in real time in the cloud and is bidirectional stream. You see this print here? This is the exact print that you say here, okay? So as these things are executed in the work in the customer worker, you can see that in real time. And you can see how fast it is to process 20 million rows in this case along 2 containerized functions. But I want to show you, because it will turn out to be useful later, is like, what happens if you're, I want to, I don't know, change a Python interpreter here. Let's change the DuckDB function. And the typical scale-up example of a data science project is, I'm happy with this. Can I just run it with 1 more month? I'm happy with the 2 weeks or 3 weeks window. Can I just run the exact same code, just scaling this up? And the way in which you do with Bauplan, just you change it in the code. You just do Bauplan run, and this system is already up and running. So the containers of the new DuckDB version has already been built, and the system is going to pick up and scale up to get the larger dataset size in, and to then do the processing that actually needs to happen. Again, all of these apps, you see, now we have 40 million rows. All of these happens automatically and in the cloud for me with several benefits that we're going to highlight. Again, there's way more things to be said about the platform, but just want you to get the feeling of the developer experience that you get once you invest in understanding a specific workload and specific use cases. So let's go a bit into details into these three phases. Phase number one, planning. What do we need planning? Again, Bauplan abstractions are easy to understand for data scientists, they're easy to write, but it also means that the system needs to somehow fill the gap between you saying, I want pandas 2.2, and my function in the worker is a Dockerized function that has exactly that version. And that goes, of course, for the data, right? When I specify transaction, there's actually a table in some object storage. And what actually needs to happen is that I need to know what is the range byte reading that the system needs to do to satisfy those filters. So how do we go from one to the other? And the way in which we do it, and we call it planning in analogy with the DB literature, is that we have a logical view first, which is basically just taking what the user gives us, parse it out, understand which function goes first and which function goes later. You saw the in the demo, the normalized strip first function, and then the group by later. And then we produce what's called a physical plan, so a physical view. The physical view is the logical view enriched with system function that the user do not write, okay? But function that allow the system to fill the gap between what is the logical view and what actually needs to happen in the sense of Dockerized operation and S3 operation. So for example, in this case, we're gonna have a system function which reads from Iceberg, the open format, S3 compatible format for tables. We're gonna have Docker with pandas and different Python interpreters, and we're gonna have Iceberg at the end for writing again. And then finally, there's a worker view. Because when we ship things to a specific worker, it may be that the worker already has at his disposal some of these artifacts. For example, maybe some of these files from S3 has already been downloaded by a previous colleague of mine, so there's no need to rerun it. And maybe the package has already been installed by somebody else, so there's no need to redo the entire pip install on that. And that will result in significant gain. We're going to see that because aggressive caching in a team may actually skip users a lot of waiting time. And the great thing is that because of our abstraction, which are completely declarative, both in the data side and in the environment side, the user doesn't need to know anything. Like the function will work, even if you're reading from a Parquet file local, if you're reading from a narrow stream somewhere else, or if you're reading from S3 for the first time. There's no need for you to change the code. It's the machine that does all of that. So the key intuition of the environment building and why it's so fast to change a DuckDB version and a Python version and rerun it is because we actually do not build a container. We assemble them from packages that has been basically downloaded in a cache before. This intuition goes back at least to OpenLambda, and we kind of take it to the extreme view by A, making it compatible to Docker, and B, exploiting the fact that all our users, so data engineering, is done primarily in SQL and Python. So by restricting the number of language and runtime that we need to support, we're able actually to provide incredible optimization. That has a bunch of advantages. One, you don't need to know Docker. You don't have to install Docker in your client, and there's no bottleneck, either from PyPy or just going through ECR, for example. So if you want to add just a standard data science package to Lambda, or to a warehouse-based serverless environment like Snowpark, you may wait between 30 seconds and 2 minutes. In the case of Bauplan, as you saw, it may take less than 5 seconds if you actually need to install it for the first time. And then as soon as somebody else installs it one time and you get in the same worker, it's actually immediate. So the cache will actually work for you as well. So we're like 15 times faster than the normal serverless options. And the second big part is about data movement. As we discussed, use cases for data serverless are very different than hundreds of milliseconds small functions. We're moving hundreds of millions, billions of rows, tens of gigabytes moving in and out of functions, and functions takes quite a bit of time to do all their processing. How do we make it faster? And a key intuition of our design is that we restrict things that go inside the function. The only thing that our function can read are tables, and the only thing that the function can output are tables as well. And we restrict the format of this to be arrow. For those of you who are not familiar with it, arrow is becoming kind of the de facto standard for in-memory and over-the-wire layout for tabular data. And it's a project that has been started by Pandas creator Wes McKinney a while ago. Now it's a growing ecosystem, and Arrow bindings are available for all the most popular language. The key intuition about Arrow is that Arrow allows zero copy in different part of the stack. And zero copy is of paramount importance to get the performance that you saw during the demo, because a significant amount of time for people working with data is just waiting for the data to be available. So in the first sense of zero copy, Arrow allows zero copy between functions that are co-located in the same host. So if the children function are co-located with a parent function, there's no need to copy the entire tables from the parent process to the children process. The children process can just get a pointer to the memory location, and they just can read it immediately. Which means that compared to the typical, hey, I save something as a side effect on I/O to S3, and the children functions read it back, you can be, even 100 times faster in that particular case. The second advantage is that if you have different workers, so you need to send data somehow, Arrow has no serialization or deserialization cost. So since everything in Bauplan happens within the cloud, so your code is local, but then it gets shipped to run in EC2s, EC2s can exploit the EC2's bandwidth to basically send each other data. It turns out that sending between machines an Arrow stream of a table is as fast as reading a local Parquet file because of the cost of serializing data tables. Finally, and I point here to a paper that we just published at Big Data 2024, Arrow fragments can be combined as logical view for downstream children. What does it mean? Take, for example, the use case of scale-up data science runs. I first run something for January, and now I want to try for January and February. If the system is smart enough, it's not going to download January and February the second time, because it already knows that January is somewhere in the worker cache. And Arrow allows to basically concatenate table without copying between January, the one that we already downloaded for a previous run, and then February, the differential part of this. And then the downstream children function will just read it as a normal Arrow table with no code change or no difference. So if you're interested in caching, please check out our latest paper. In preliminary benchmark, even if it's not a very good sequential use cases, but everybody know the TCP in the data engineering community, we can save up until 30% of S3 reads just because of this ability of combining fragments and differentially caching stuff. So to wrap things up, we decided to co-design abstractions. So the only thing you can do in Bauplan are functions that takes data frames as input and output data frames, and runtime feature. So everything is an Arrow table basically, and you can always express your transformation in Python. See, but by basically constraint and narrowing down to industry-inspired use cases, our platform, we're able to provide not just better performance, but a much more ergonomics, fast experience to data practitioner. It's important, I think, to notice that, while the company is still small and Bauplan is still technically in beta, is already in use by large organizations making more than $1 billion a year, next to much more mature data platform in that sense. Of course, I just could touch on a tiny bit of all the things that we discussed in the paper, both on the design phase and on benchmark comparison and more industry traces. So if you're interested, please check a look at the paper and send me a message. And of course, we look forward to sharing a bit more of what we're doing as the platform progresses and we collect more and more data from our user. In particular, we're working heavily on further memory optimization, which, as you can guess, moving around so many big data frames is an important component of the entire platform. And of course, function scheduling. Like our environment are single tenant, which is different than most serverless platform like Lambda, which introduce completely different constraints and completely different opportunities and challenges when you think about scheduling, less, like a fewer function, but much bulkier, much bigger function in that sense. So thanks so much for your attention, and I'm happy to answer any question you might have.
Thank you very much, Thank you very much. So we can follow the same dynamics of before. If you have questions, just like if you don't want to get close to here, I will repeat them. If not, you can get here and ask them personally. Thank you very much. So we have a question here.
Hi, this is Max. So you're bringing functional computing to serverless, and I was wondering, there are a lot of optimizations for functional computing. Did you ever consider these, or do you have any guess if there can be even more increase in speed?
That's a very good question. So right now our functions are, sorry, our DAGs are almost purely functional. There's a bit of trickery there when you need to pass parameters and so on, which we couldn't go into it. And it's mostly to make our life as planners of this function easier. We don't really go into what happens inside of a function. So inside of a function, the code that our user typically write is typically Python imperative code with pandas or polars or SQL or DuckDB or stuff like that. It would definitely be interesting to go one level below and kind of try to nudge some of our users to write their code in a specific way. Right now, our philosophy is if you have a Python function in your notebook that used to run on your computer or on Databricks or whatever, you can copy and paste it into Bauplan, add a decorator, and it should work exactly the same. But of course, we look forward to, once we get a bit more known, we look forward to be able to nudge our user to change something a bit to make it more performant.
Yeah, thank you. Nice.
So it seems we have not any more questions, do we? Personally, Jacopo, I love your background. It's very
thank you.
yes,
Thank you. Yes,
kind of historical.
Yeah. As a yes. I'll let you decide if this is a elaborate Zoom background or the actual place where I live.
Exactly.
I'm not gonna reveal the answer to this, so you can you can see what AI can do, or you can believe that this is still the real world. It's up to you.
Very good. I love it. I love it. Thank you very much. So it was very interesting. Thank you for being here and giving your talk. And so if people have further questions, you can read them in the Discord channel.
Yeah, thank you very much. I saw people are very happy about our titles, and so
Yes,
which is something that I've always been proud of. If you look at my Google Scholar, I'm mostly famous for that. So thank you for appreciating the irony.
Make sure at least I will take a look at it because it's promising. Yes. So thank you very much, Jacopo. So next one is there we are, Runjie with GraphQL versus REST.
Yeah.
Which is also a remote presentation. So we can hear you, we can see you. So begin whenever you want.
Okay.
Thank you, Ray.
Well, hello everybody. My name is Runjie, and today I'll be presenting our study GraphQL versus REST, a performance and cost investigation for serverless applications. Here's the outline of what this presentation will be covering. So let's get into background and motivation section. So we have heard quite a lot about serverless today, but still, let me walk you shortly through the main features of serverless. Serverless services are now provided mostly by some cloud providers like AWS Lambda and Google Cloud Functions. These providers function as a service or FaaS on their platforms and offer many tempting features, like we don't have to manage the underlying infrastructure anymore, and there are automatic scaling to handle bursts of requests, and we can know our bills by exactly how much time and resources we used. So a typical REST-based serverless application architecture can be represented by these three layers: client application, API gateway, and the working serverless function. So, well, although REST is good and has been adopted broadly in today's web applications, it is not without its problems, and most notably overfetching and underfetching problems. In overfetching, the application retrieves more data than it actually needs, so more bandwidth and computing resources are consumed. And in underfetching, the application has to run multiple API calls to gather all the data, and that leads to longer round trip time and more complex logic on the client side. So the problem will cost you and your serverless applications performance, resource usage, and at the end of the day, maybe more importantly, the bill you will pay to the providers. So for this study, we are looking into the possibility of using GraphQL as an alternative to REST-based applications. So GraphQL was initially developed by Facebook and open source in 2015. The key benefits of GraphQL includes precise data retrieval as controlled by your application's specific needs when you are querying the API. You can aggregate individual REST function calls and gather the request result in one round trip. And strong typing systems thanks to GraphQL schema design. And also a bunch of other features which we didn't use in our experiments, but could be important for real-world applications like real-time APIs. Also, at the same time, GraphQL is gaining attention in recent years. It has become more popular in the industry, and companies like GitHub and Netflix are starting to use GraphQL as an alternative to REST APIs. So with that, now we move into our research questions. For this study, we have two research questions. Research question one is about GraphQL and its performance. We want to know how well does GraphQL perform in serverless environments, and specifically, how does it compare to REST APIs in terms of round trip time and cost? And in research question two, we look into how managed GraphQL service compared to unmanaged ones. How well does a GraphQL service provided by cloud providers like AWS AppSync compared to our self-hosted ones like the Apollo server? So next is a description of the methodology we used in our experiments. For now, we are using an image processing pipeline application as a demo to study how GraphQL compared to REST applications in the serverless environment. The pipeline presently has 7 independent serverless functions. Each is supported by an AWS Lambda function and does their individual job, like rotating, flipping, and cropping images. We're putting the images right now in the request payload, and to stay below AWS services payload limits, we chose an image slightly smaller than 5 megabytes. And we can configure how these 7 functions or image filters are arranged in the application. As far as we can tell, the demo is quite good for our comparison. We have good amount of computation work to do, and the I/O takes quite some efforts. The workflow has multiple stages, so it features a real-world processing application pipeline. And we can easily extend it for new features like adding more image filters in the future and processing different formats of files. So to compare GraphQL and REST, we have 2 sets of implementations. One is the GraphQL way and the other is the REST way. For GraphQL, the REST is responded with a single request response, and the pipeline orchestration is done internally within the GraphQL server by its resolver function, which is GraphQL's internal function for aggregating data. And for REST, the request is handled mostly on the client side. The client is in charge of arranging workflows, and there could be multiple round trips between the client and the cloud. Also, for the REST implementation, we try to minorly different way with and without API gateway to look into how that influence our REST application's performance. And when it comes to testing, we have a detailed infrastructure description for our testing environment. It has mainly 3 parts: the serverless backend, the GraphQL servers, and the test clients. For the serverless backend, we have AWS Lambda functions that does the actual dirty works. They are specially chosen to use ARM64 in order to avoid hyperthread variances as happen on Intel CPUs, and the functions are written in Python. The API gateway is also used for easier integration into other AWS services like Lambda function, AppSync, databases, and more. For the GraphQL servers, we have the managed AWS AppSync version and the unmanaged Apollo version. AppSync is Amazon's GraphQL service. It is fully managed with auto-scaling, easy integration into Amazon's internal services, and easy billing. Apollo server, on the other hand, is arguably the most popular open source GraphQL implementation nowadays. We were hosting it on an AWS EC2 instance in the experiments. For the test clients, we have 4 settings. The first is a local desktop located in the Washington state with fair amounts of memory and processing capability, but the bandwidth is limited, which mimics the typical school or home setting. The second is an AWS EC2 instance as our client. It tests the performance when the client and the server are in the same cloud. And the third is a Google Cloud VM instance. It tests the performance when the client and server are in a different cloud. And finally, we also use AWS Lambda function as clients to scale up concurrency and see how that influences different service performance. So now let's get into the results part. To jog your memory, in research question 1, we were trying to compare GraphQL and REST APIs in terms of round trip time. For the first thing, we are looking into the round trip performance between different clients to the Apollo and the REST server. We have the local desktop clients in the Washington state, the intercloud Google VM, and the intracloud AWS VM. Well, as it turned out, when using Apollo accompanied with API gateway, we were consistently getting best performance, most likely thanks to API gateway's ability to better distribute the request burden. And as we move from left to right in the graph, the network latency is gradually improving as we move from local to different cloud to the same cloud. And the performance of all 3 settings were becoming better. But GraphQL does show the biggest advantage in high latency scenarios on the far left, like our everyday life, home, school, or out in the field. And when the testing is done inside the same cloud, which is AWS, where the network latency is very low, the benefits of GraphQL doesn't seem to be that much. But we also look into individual round trip time distribution for the 3 experiment settings, Apollo and API gateway, and REST under different concurrency levels. On the low concurrency, with very few threads running, the cold start causes Apollo server to have a quite high variance. When we are moving to higher concurrency counts, the whole thing looks more like a typical normal distribution with something around 5 to 8% variance. And specifically on the 70 concurrent threads for Apollo and API gateway, we were seeing a near bimodal distribution. And it turned out that that's because around 15% of the requests were processed by Apollo at the end of the running batch, so they're gaining like more resources than their predecessors. For research question 2, we were trying to see the performance and cost differences for hosting GraphQL APIs with a managed and unmanaged GraphQL server. This graph above is the round trip time for managed AppSync and unmanaged Apollo server when we are trying to push to very high concurrency level. The client we used for this experiment is Lambda functions as clients, since no typical VM can support this level of concurrency without performance degradation from the client side. So the unmanaged Apollo server shows a slightly better performance up to around 54 threads. but the round trip time just grew indefinitely from that point. So obviously there's a scaling problem for our self-hosted Apollo server. You can probably address that with a better VM, but that will only push like the 54th thread point a little bit later, but that problem will come anytime. AppSync, on the other hand, handles the level of high concurrency pretty well. And thanks to the AWS automatic scaling, you don't have to worry about the concurrency problem, even with lots of requests incoming at the same time. AppSync does show some other interesting patterns as we go beyond 160 threads. Although the average running time is still stable, the variance became much higher. So potentially AWS, underlying the AppSync services, AWS is using a large enough VM to support it, but all it really is requires some further inquiry. So the implications here are that choose AppSync or a similar managed service when there is a high scaling need. Self-hosted Apollo can be extended and improved, but that needs more effort into infrastructure building. And we were also estimating the cost for the different ways of services, REST, Apollo, and AppSync. The cost estimation here includes compute costs for the serverless functions, the cost of data transfer, and the cost of providing the APIs. So as it turns out, managed GraphQL service or AppSync is much cheaper than the unmanaged Apollo server and also beats REST slightly. It costs about $4 per million requests, while for self-hosted Apollo, it's around $63, calculating the VM hosting price. So when you're trying to deploy a real-world GraphQL server, the deployment choice should be made considering how much freedom you want when it comes to using GraphQL. If you need to handle high concurrency and it's okay with AppSync's internal setting procedure, then AppSync is a go-to. But if you want more freedom on hosting choices and the concurrency level is not too high, you can also try Apollo and a similar open source solution. So that brings us to the conclusions part. We had two research questions. How well does GraphQL perform and how does a managed GraphQL server compare to an unmanaged one? We conducted experiments with the AWS as a major backend server and use different clients to compare the results. As it turns out, GraphQL consistently outperformed REST, most notably under high latency. Using API gateway helps to reduce round trip time a little bit. And but when it comes to cloud native setup, GraphQL doesn't seem to help that much. For the unmanaged versus managed comparison, AppSync showed much better stability and performed better beyond 54 concurrent threads, and the price for AppSync is also much cheaper at $4 per million request. So a few deployment recommendations if you want to try GraphQL. The first is that in high latency scenarios like edge computing and mobile applications, GraphQL is definitely recommended. If you have needs for large scaling, try some mature services as provided by large cloud providers. And if you have very specific control needs, want to better manage the underlying server and maybe change a few details in the implementation on the low concurrency level, you can also try Apollo server as the open source implementation. Yeah, this concludes my presentation. Thank you all for listening. Any questions?
Okay, so any questions on this? Very interesting presentation once again. Could you please return to the plot on the cost of Apollo against AppSync? There we are. Because there is something I don't get, like it seems the numbers in the cost comparison do not fit the ones in the...
Yeah, it's because in the graph here, I already included the cost for data transfer and
okay,
for,
yeah. So now I get it. Yeah, sure, sure.
So that's why it's not starting from 0.
Okay, perfect. No problem. Yes. Sure. Perfect. So does anyone have something to say? So thank you very much, Runjie. That was very interesting. People may ask questions through the Discord channel. Just keep in touch through that. And thank you very much for being here and presenting your work. We really appreciate it. Thank you.
Thank you.
Okay. So we have the last presentation of today, which will be also remotely presented. And it is Philipp Gritsch with PlugFlow. This will be the last presentation of this workshop on serverless computing. Sorry, no, it's not a presentation; it's a demo. Sorry, this will be the last presentation in the workshop on serverless computing, a demo of PlugFlow by Philipp Gritsch. So just talk a moment. Can you talk a bit, Philipp?
Hi, can you hear me?
It's a little like distorted. I don't know if.
Try again. Is it better or?
This is better. This is better. Yes.
Okay, sorry.
Okay. But we can understand you. Like no problem. Alec, are you there? If you feel it's okay, he can go on.
Okay, thank you very much.
Yes.
We can understand you. Yes, you will
Perfect.
see in the recording what was it, but no big problem. Go ahead.
Okay, go ahead.
Okay. Is it my? Okay, good. I just checked with my colleague if it's fine. Perfect. Okay. So hi everybody. My name is Philipp Gritsch. I'm happy to present this demo about PlugFlow here at WoSC10. And PlugFlow is our current tool which we are working on. And it's targeted towards serverless workflows. Those workflows are usually composed of serverless functions written in different languages, deployed on different platforms, and we execute them using a workflow management system. Here is a short example of such a workflow. We have a fetch paths function which fetches some paths from the storage. Afterwards, for each path, we perform a transform image operation, and afterwards, all the results are merged and stored. Here, note that each function is deployed on a different platform, and the map control flow element is a workflow management system built in. However, here we already see some common issues. Small functions come with the same overhead as large ones, not only in terms of code and warm start, but also in terms of dependency management and deployment. And flow options are limited to what the workflow management system supports. If we have a workflow which has some conditionals, we have to make sure the workflow management system supports conditional branching. We tried to overcome these limitations by giving developers more control. Concretely speaking, we let developers plug small functions directly into the engine, and using also these small functions, we allow them to create custom control flow elements, like map or parallel. Furthermore, workflow developers are able to encode workflow logic directly within those functions to remove the need for a separate workflow language. Our system PlugFlow is a hybrid approach to compose and manage workflows. Using the system, we can convert short-running functions to plugin functions, but we can also convert workflow manager or usually built-in control flow elements as plugin functions. But before we go into details about the plugin functions, let me show you how developers can code their workflows. And they do so, or we do so, by letting the functions decide what's next. In this short example, there is an initiate or a registration workflow. The first function, initiate registration, has some condition it needs to check. If the condition succeeds, we forward the action to register, otherwise the request is rejected. In the code, this is how it works. So in the return statement here, we can see the usual payload, but also a field next, which dynamically describes which function should be executed next. With this concept, I can show you how we can use plugin functions as control flow elements. In our previous workflow, fetch paths would indicate with its next field that the next operation should be a map block with a transform image operation, and for the reduction we use merge and store. How we code it is like this. So every developer who wants to build a custom control flow element such as map has access to the parameters passed as part of the next field, in this case transform image and merge and store. Our demo implementation now invokes the function for each element in the payload and afterwards forwards the result to the reduce function. Using that approach, developers can create custom control flow elements, giving them advanced possibilities to design their workflow and perform optimization, such as tree-based merges in this example. Now let's see a short demo, which was pre-recorded, and showing how easy PlugFlow is to use. So in the first command deploys the workflow, which is given as code files in the directory, and the second run command runs the workflow as such. Now we see fetch paths is now a plugin function directly executed on the engine itself. So it takes only 8 milliseconds. Afterwards, map performs the true transform image operation, and afterwards merge and store concludes. We are also currently working on a web UI, which enables the same feature only on the web, enabling for easier control and management. And that was it. To sum up, PlugFlow is our tool which we are currently working on. I hope you liked the demo and find the concept useful. I look forward to see the recording of all your sessions, which I didn't have the chance to see here in Europe. Thank you very much. Of course, I'm happy to answer some questions.
So thank you very much, Philipp. Do we have questions here in person? I was thinking maybe it's kind of out of context discussion, but do you support kind of complex communication patterns or something for functions like joins or something? I don't know, like kind of it's more specific on SQL and these kind of things, but maybe.
So currently, I mean, the presentation doesn't show up.
So
I mean, the developer can choose everything, but we are working on a function to management system communication channel. So each function can communicate with its manager, and by that we hope to enable some sort of graph processing problems. But that is future work. We're currently looking into that and also applications.
Okay, very good, very good. Are you planning to publish this, or is it just an internal